Hello, everybody. Professor Barlow here, Northampton Community College, Physics 215, calc-based physics, physics for scientists and engineers. I'm going to pick up on chapter 17, which is temperature, thermal expansion, and ideal gas law. Before I get started, here, I just want to note that chapter 13 was the last chapter we did, fluids. So we're jumping ahead. We're skipping chapters 14, 15, and 16, and we're jumping right into chapter 17. I'm hoping that a lot of this will be familiar to people who have taken chemistry at the college, or any college chemistry class, or even a high school chemistry class. It should be a review. If it's not, keep track of your questions and answer them in the Zoom, ask them in the Zoom meeting so I can answer you, or send me an email. So we're going to talk about temperature, thermal expansion, and ideal gas law. The picture there, the hot air balloon, the way that works is the balloon has that little heating element, above the basket. And what it's doing is it's heating the air, causing it to expand. And it's also causing air to come out the bottom of the opening of the balloon. It does two things. It expands what's going up into the balloon, but it also, it reduces the amount of air inside the balloon itself, which means the density is lower than the outside air, which causes the balloon to rise. So we'll talk a little bit about why that happens. So we'll briefly touch on atomic theory of matter, then we'll go over temperature and thermometers and the different temperature scales. We'll talk about thermal equilibrium. We'll talk about thermal expansion and thermal stress. Thermal expansion and stress are really the two topics that are engineering statics related. Gas law and absolute temperature, and then ideal gas law. So we'll spend a little bit of time deriving or working our way up to the ideal gas law. We'll do a couple problem solving things, and then we will look at ideal gas law in terms of molecules, or look at Avogadro's number and what that is. And then the ideal gas temperature scale. So atomic or molecular masses are measured in unified atomic units, or unified atomic mass units. That little script U is the symbol for lowercase u is the unified atomic mass. This unit is defined so that carbon-12 has a mass that is exactly 12 atomic mass units. Expressed in kilograms, one atomic mass unit is 1.66 times 10 to the minus 27th kilogram. So motion on an atomic level is very jittery, almost like tiny flecks in water. They're the result of collisions of individual molecules, okay? On a microscopic scale, when you take a look at different substances, right? Up here would be solids, in the middle here would be what liquids look like on an atomic level, and over here are gases, okay? And each one is quite a bit different, and they behave quite a bit different. The first example we're going to take a look at is what's the distance between atoms. So we're given the density of copper is 8.9 times 10 to the third kilograms per meter cubed. So each copper atom has a mass of 63 unified atomic mass units. Estimate the average distance between the centers of neighboring copper atoms. So let's switch over to a whiteboard. Take a look at this. So what we have is, if we were to look at what we're given, if we had a 1 meter by 1 meter by 1 meter cube, it's 1 meter on every side. So the volume, 1 times 1 times 1, would be 1 cubic meter. We know that mass is equal to density times volume. And we also know that 1 atom of the copper is 63 units. Well, they gave us what the equivalent is in kilograms for one of these atomic mass units. So if I want to go from atomic mass units to kilograms, 1 atomic mass unit is 1.66 times 10 times 10 to the minus 27th kilograms. And that is the mass of 1 atomic mass unit. So that cancels. So I'm left with that 1 atom of copper is 1.05 times 10 to the minus 25th. That's just multiplying 63 by 1.66 times 10 to the minus 27th kilograms per atom. So volume, if I rearrange this equation, volume is going to be density divided by mass. In the problem statement, they gave us the density of the copper. The copper is 8.9 times 10 to the third kilograms per meter cubed. And we also know from up above here that each atom has a mass of 1.05 times 10 to the 25th kilograms per atom. So its density we're given as kilograms per meter cubed, and this mass that we determined, we have kilograms per atom. So when I do this division, right, I end up with a volume of 8.5 times 10 to the 28th. So I'm taking a relatively large number and dividing it by an extremely small number. When you divide by an extremely small number, you get an extremely large number. So 8.5 times 10 to the 28th, the kilograms cancel, and when you do the division, the atoms come up. So you end up with 1 atom of copper. I'm sorry, that's the number of atoms in 1 cubic meter of copper. So in 1 cubic meter of copper, there is 8.5 times 10 to the 28th atoms. Okay, so this is per cubic meter, right? Well, if I were to take the cube root of this, or raise this to the 1/3 power. Same thing, taking the cube root or raising it to the 1/3 power, right? So if I take this 8.5 times 10 to the 28th atoms per meter cubed, what we're left with, right, is 4.40 times 10 to the 9th, right? So if I take the cube root of that, I end up with the number of atoms per side of this thing. So there's 4.4 times 10 to the 9th atoms per side. So if I want to know the spacing, I have 1 meter is the length of one of the sides. If I divide that by the number of atoms per side, I'm going to get the spacing between the atoms, which 1 divided by 4.4 times 10 to the 9th is 2.3 times 10 to the minus 10th meters. That's the spacing. Okay, so actually that's more of a geometry problem than a physics problem, right? Okay, so why is this important in a physics class that engineers need to take? Well, it's extremely important because temperature is a measure of how hot or cold something is, but that temperature will yield, it will lead to, it could lead to, I should say, expansion or contraction of the material, right? That's why if you've ever driven across a bridge, at the ends of the bridge, there's usually a seam. Now here they have, you know, this metal sawtooth thing that allows the bridge to flex up or down. Now, even if you don't see this, there's other materials that they use to allow for expansion and contraction and movement. You know, some bridges, it's more of a very thick rubber gasket type material, but it allows the bridge to expand and contract so it doesn't crack and damage it. So let's talk about temperature scales. So thermometers are any instrument used to measure temperature. So some very early ones that seem to be getting kind of popular again are these liquid-filled ones. A lot of times you'll see these in catalogs and things. So those were very early ways to measure temperature. The individual glass elements that make this up, they're usually in water, and then there's usually alcohol or some other material in them that, you know, that tells you the change in temperature. There's other thermometers out there, liquid and glass. So when I was young, and you can still get them, but they're more for like academic type settings. Thermometers that are filled with mercury, you don't see them much. I don't think you can buy them anymore. There's usually like a red liquid. It's probably alcohol or something that it's filled with, and there's a bulb at the bottom that acts as a reservoir. When it gets hot, it expands, and it's calibrated to, you know, the markings on the side of it. The one for your oven, it depends. Older ovens like this one here, it's called a bimetallic strip. So if you look at this, you see this coiled up piece of metal. As it gets hot, right, it expands, right? And as it gets hot, you know, it tells you where on the dial the temperature is. Okay. Most of the time, and we'll talk about kelvins at the end of the chapter, but most of the time temperatures are reported in either Fahrenheit or Celsius, right? Two common points that you have to reference back to, right? Freezing point is either 0 degrees Celsius or 32 degrees Fahrenheit. And boiling water is either 100 degrees Celsius or 212 degrees Fahrenheit. So before I do this, I want to go over two equations that you're going to want either on your equation sheet or handy or whatever. If you want to know the temperature in degrees Celsius, if you want temperature in Celsius, but you're given Fahrenheit, here's the equation that you're going to use. 5/9 times the temperature reported in degrees Fahrenheit minus 32 degrees. So if I give you Fahrenheit and I want Celsius, you plug Fahrenheit in here and you get Celsius. If you want Fahrenheit and you're given Celsius, well, you could plug the number in here and do the algebra, or I can just give you the algebra. 9/5 times the temperature in degrees Celsius plus 32. All right. So you can see I'm just bringing the temperature 32 over to the other side and multiplying it by the inverse of 5/9. So those are your two temperature conversion equations. All right, so if we want to do an example of this, if you take your temperature, normal body temperature, and since COVID, we've been doing this a lot lately, right? Normal body temperature, 98.6. What would that be on a Celsius scale? So 98.6 is degrees Fahrenheit is what we normally report in the US. If you go to Europe or most other countries, temperatures are commonly reported in Celsius, not degrees Fahrenheit, okay? So what's 98.6 on a Celsius scale, right? So if we're given Fahrenheit, degrees Fahrenheit, and we want to go to degrees Celsius, I'm going to use this equation. So it's going to be 5/9 times 98.6 degrees Fahrenheit minus 32 degrees .6 in Fahrenheit is 37 degrees Celsius. So just simple algebra. Nothing exciting there, right? So temperatures and thermometers. A constant volume gas thermometer depends only on the properties of an ideal gas, okay? Those properties do not change over a very wide variety of temperatures. Therefore, they're extremely accurate, and they are used to calibrate other types of thermometers based on other materials. So you have some gas over here, you have reference marks right here, and then you have mercury and a hose connecting the two sides of this thing, right? So this is a picture of a constant volume gas thermometer. Okay. Two objects placed in thermal contact with one another will eventually come to the same temperature. When they do, they are said to be in thermal equilibrium. Okay, so thermal equilibrium is the point at which you arrive after I have something hot, something cold, you put them in contact with one another, they'll eventually reach the same temperature. That's thermal equilibrium. The zeroth law of thermodynamics states that if the two objects are in equilibrium with a third object, they are also in thermal equilibrium with one another. Okay? Kind of like, if you think about what that's saying, if you have two objects that are in equilibrium with a third, right, they're also in equilibrium with each other. So, I mean, I think that makes sense intuitively. To be honest with you, I'm not quite sure why they had to make a law about it. And even so, I'm not even sure why they called it the zeroth law. Why don't we just call it the first one? Anyway. All right. Let's look at thermal expansion. Okay, this is the type of stuff that's important to an engineer. Linear thermal expansion occurs when an object is heated. So you have some object at a starting temperature. So its initial length is going to be L0. Its temperature initially is going to be T sub 0 or T naught or L naught. Okay. When you heat this up, right, you will have a change in temperature. If you cool it down, you will also have a change in temperature, but if you heat it up, you'll have a change in length. It's a positive change in length. If you cool it down, okay, you will have a negative change in length. It will shrink. It will get smaller. Okay, so the equation for this is the final length is equal to initial length 1 plus, and this symbol right here is called the coefficient of linear expansion. It's a proportionality constant, okay? It's a lookup, or it's something that would be given to you. It varies by material, okay? You take that, you multiply it by the change in temperature, that gives you the change in overall length. Or this whole equation gives you the new length. This right here, multiplied by L sub 0 will give you the new length. Okay. All right. So, coefficients of expansion. So, coefficients of linear expansion. Notice the units, they're in degrees C to the -1. So, if this table is reported in degrees C to -1, and I give you temperatures in Fahrenheit, you have to convert the temperatures from Fahrenheit to Celsius to use these coefficients in the previous equation. So just be careful with that. We'll talk about volumetric expansion in a bit, but the values are listed in the same table. This is table 17.1 in the textbook. Okay? So looking at a bridge example, you have a steel bridge, suspension bridge, 200 meters long. Temperature is 20 degrees Celsius. If the extremes of temperature to which the bridge might be subjected, okay, are 30 degrees C is the lowest and 40 degrees C is the highest, how much will it contract or expand? Okay. So let's look at the expansion and contraction, together. Or actually, let's look at them separate, and then we'll sum them to see what the total expansion and contraction could be. Right, so I'm going to clear this. Notice that the temperatures are listed in degrees Celsius, so we don't have to do any conversions there, right? Delta L, change in length, is equal to the coefficient of expansion, right? L sub 0 delta T. Okay. So change in length is equal to your coefficient L naught delta T. Okay. if you look up steel in the table on the previous, on 2 slides previous, you'll see that it is 12 times 10 to the minus 6 per degree Celsius. 200-meter long bridge. The highest that the temperature could reach is 40 degrees Celsius. And our reference is 20 degrees Celsius. So if we do this, we get 0.048 meters or 4.8 centimeters. Now, I just took the equation and rearranged it to get this. You can put that on your equation sheet to get change in length, right? Or you could end up with, or you could use the first equation, get the new length and subtract the new length from the original length to get the change in length. So it's either one. You can have both on your equation sheet. So to get how much the bridge would contract on a cold day, it's -30, right, minus 20 so it would be 0.12 meters, or up to 12 centimeters it could contract. So overall, so this would be expansion on a hot day and contraction on the coldest day. This thing could move 12.8 centimeters over its 200-meter length. Okay, that's the clear reason why you need expansion joints in a structure like that, so that it can expand and contract. Now that's over its entire length, right? So, you know, you look at the bridge in segments and you look at the expansion and contraction in segments, okay? So most bridge joints, you're not doing 12 centimeters in a single bridge joint. You're doing a whole bunch of bridge joints over a 200-meter span to break that up. So, conceptual example. We'll do an example where we'll apply some numbers to this next, but do holes expand or contract? If you heat a thin circular ring in an oven, does the ring's hole get larger or smaller? Well, the whole ring will expand or contract. It's not that if you subject this whole thing to heat, to the same heat, like putting it in an oven, the whole thing will expand and contract, not just the inner part of the ring. Now, if you take a torch, like a plumbing torch, and you just heat the inside of it, you could theoretically get just the inside to expand a little bit and not get as much on the outside. But for the most part, when you heat it, the whole thing gets larger, okay? So an example, if you have a ring, an iron ring, it is to fit snugly on a cylindrical rod at 20 degrees Celsius. The diameter of the rod is 6.445 centimeters. So notice this is diameter, not radius, okay? So be careful with that. We're given diameters here. And the inside diameter of the ring is 6.420. Now notice that the rod is slightly larger than the ring at 20 degrees Celsius. To slip to slip over the rod, the ring must be larger, obviously, to fit over the top of it, by about 0.008 centimeters. So it can't be exactly 0.6445. We got to add a little bit to it so that it goes over the top of. So at what temperature? So how much do we have to heat this thing up to such that it be brought that the hole is large enough so that it fits, the ring fits over the rod, okay? So I'm going to clear this, okay? The equation that we're going to be using is your change in length is equal to coefficient of expansion, initial length, delta T. Okay. Looking up iron in the table for the coefficient, it is 12 times 10 to the minus sixth per degree Celsius. We're given a diameter. Well, we're also given a starting temperature of 20 degrees C. We're given an initial diameter of for the rod .00645 meters. So that's the rod. Okay. We need to increase this, okay, in order for the ring to fit over the rod. We need to add 0.00008. That's 4 zeros. We need to add 0.0048 meters to that. So the ring, right, we need to get the ring up to a diameter of 0.06453 meters. So this is what we need to get to, okay? But our original ring is 0.06. So I'm doing the conversion right away from centimeters to meters. You can do the calculations in centimeters and then convert it to meters once you plug back into this equation and do it once. It's 6 of one and half a dozen of another. Okay, so that's what I want to get to. That's what the ring currently is. So my change in diameter is 0.00033 meters. So at that point, I have what I need to just plug back into this, right? The 12 times 10 to the minus 6 per degree Celsius, that's just a table lookup. The change in length that I want, right? Well, okay, let's start here. The change in length that I want is my 0.00033 meters. That's going to be equal to the 12 times 10 to the minus 6th per degree Celsius. The original length is the original diameter of the ring, which is the 0.0642 meters. And we want to find the change in temperature, right? So pretty simple algebra. Our change in temperature we need is 428 degrees Celsius. If we have a starting ambient temperature of 20 degrees, we got to get this rod to 448 degrees Celsius. Right? So how many family members have you seen, mom, dad, grandma, granddad, and whoever? Have you ever seen them take a jar that they can't get open and run it under hot water? Okay. When the lid of a glass jar is tight, holding it under the hot water for a short time will make it easier to open. Well, the lid is going to heat up because the lid's metal and the jar is glass. The metal will heat up and it will expand faster than the glass. So it gets just ever so slightly bigger for a very short amount of time. It makes it just that much, just a little tiny bit easier to open. Okay, volumetric expansion. It's very similar to linear expansion, except we're going to be dealing with gases and liquids instead of solids. So the previous equation, what we've done up to this point, is anything that's a solid. Volumetric expansion works for liquids and gases, and that's the equation, right? The coefficient here, right, that script B, is volumetric expansion. And it was given in the same table that we looked at before. If you look at the values for solids, the volumetric expansion is about 3 times that of linear expansion, okay? Roughly, okay? So we have a gas tank, okay? Gas is a liquid. You have a 70-liter tank, steel gas tank of a car. You fill it to the very top with gasoline. So you can't really do that. There's mechanisms that you can't really do that in most vehicles. You can't go up into that filler nozzle. At any rate, okay, so you have a 70-liter tank filled to the very top with gasoline at 20 degrees Celsius. The car sits in the sun, and the tank reaches a temperature of 40 degrees Celsius. Very hot day, 104 degrees outside, okay? How much gasoline will overflow from the tank? So that's the change in volume, right? So let's switch over to a whiteboard and run through this quick. Okay, so our change in volume is going to be our coefficient of volumetric expansion, initial volume, and change in temperature. So our volumetric expansion, the 35 times 10 to the minus 6th. So let's go back and take a look at the table. There we go. So what is expanding here? Okay. You have the tank and you have the gas. So you have two things that are going to expand, but they're going to expand at different rates. So if you take a look at this table, right, the coefficient for volumetric expansion for steel is 35 times 10 to the minus 6th. So the steel gas tank is 35 times 10 to the minus 6. But the gas tank is going to be filled with gasoline. Take a look at the difference in these coefficients of volumetric expansion. 35 times 10 to the minus 6, 950 times 10 to the minus 6. So the gasoline is going to want to expand much faster than the steel gas tank. So the tank isn't going to keep up with the expansion of, so this is the change in volume for the tank. So the tank will get a little bit bigger. So if you have 35 times 10 to the minus 6th per degree C, initial volume, 70 liters, change in temperature, right? Starts off, or I'm sorry, finishes at 40, starts off at 20. So the change is 20. So the change in volume for the tank is 0.049 liters. So it didn't get that much bigger. But now let's take a look at the gas, the gasoline, 950 times 10 to the minus 6th per degree Celsius. 70 liters, 40 minus 20, change in temperature is 20 degrees. Change in volume for the gasoline, 1.33 liters. So 70.049 liters. This is the new volume of the tank, the 70 plus the 0.049, right? The gas is now 71.33. You could have also done this with 1.33 minus 0.49. 1.28 liters of gasoline will spill. Not a good thing, okay? So that's why you can't fill the gas tank to its absolute brim. Water behaves very differently from most other solids, okay? Its minimum volume occurs at a temperature of roughly 4 degrees Celsius. If it gets colder than that, it actually expands, okay? If you put a container of something that's mostly liquid, like soda or beer or just water itself, in a freezer, unless it's something that can expand a little bit like a plastic jug, if you put something in the freezer, it will expand and it will break whatever the container is, right? Water is kind of a unique thing in that respect. It's also, water in fluids is called an incompressible fluid, okay? So its behavior is sometimes a little bit different than other things. Thermal stresses. A material may be fixed at its ends and therefore be unable to expand when temperature changes. It will then experience some compressive or tensile stress that is due to thermal stress. It's due to the change in temperature. The force required to keep a material from expanding, right, is given by delta L. And if you remember, delta L is Young's modulus, right? So if you rearrange this equation from chapter 12, you get force over area, you get the stress, change the thermal expansion coefficient, right? The Young's modulus and the change in temperature, okay?
this most likely will not be on the test. It's good to know. I'm going to skip the example. You can go through it in the textbook if you want. It's a pretty basic solution in algebra. It's example 17.8 in the text. I'm not going to go over it in the PowerPoint here because I want to start talking about gas law and absolute temperature. So the relationship between volume, pressure, temperature, and mass of a gas is called its equation of state. Okay, we'll deal with gases, and gases aren't usually very dense. So you have Boyle's law, which states that the volume of a given amount of gas is inversely proportional, right? Is inversely proportional to the pressure as long as temperature is constant. So if we don't change temperature, right, as pressure goes down, volume goes up. As volume goes down, pressure goes up. So if you think about that, if you want to reduce pressure, you're increasing volume. If you want to increase pressure, you squeeze on something and you increase the pressure as you reduce the volume. Okay, so they're inversely proportional at the same temperatures. Volume is linearly proportional to temperature as long as the temperature is somewhat above condensation point. So basically, so long as it's not starting to turn into a liquid, and assuming that the pressure stays constant, right? So now we're looking at changes with volume and temperature, keeping pressure constant. So if you extrapolate the volume beyond zero, so if you extend the volume past zero, you get to some theoretical point. We've gotten close to this theoretical point, but to the best of my knowledge, they haven't quite hit it yet. They are extremely close, scientists, but they haven't reached it yet. If you were to extend that temperature scale, like lower and lower and lower and lower, till you got to a volume of zero, okay, that is absolute zero. It occurs at negative 273.15. So for the purpose of most of these calculations, we're just going to use 273, okay? The concept of absolute zero allows us to define a third temperature scale, kelvins, right? The Kelvin scale starts at 0 degree Kelvin at absolute zero. Okay, otherwise the same as it's essentially the same as Celsius, but it's offset by that 273 degrees, right? The freezing point of water is 273.15 in kelvins. Okay, boiling point is 373.15 in kelvins. It's just a 273 degree shift from Celsius. Okay, so it's important that you understand how to convert to kelvins, and I'll explain why here next. So the last thing that we're going to look at is when volume is constant, the pressure is directly proportional to the temperature. So what does that mean? If I increase the pressure, the temperature goes up. If I increase the temperature, the pressure goes up, and vice versa. If I decrease the pressure, temperature goes down. If I decrease the temperature, pressure goes down. Okay. So why would you not throw a closed glass jar into a campfire? Okay, I'm a scoutmaster, and this drives me. You don't throw anything into the campfire other than firewood. Okay. The main reason is because you put something in the fire, things are going to expand. Okay. If you try and cook a can of baked beans and just put it in the fire,
somebody is going to get hurt because that's a metal can and it is going to get hot to the point where it's going to burst. Bad news. Even rocks. Kids will do this because they want to see if it works. If you have a rainy day and you take a rock and you put it in a hot fire, the rock could crack because of the water that seeped in during the day. So you don't even throw rocks into a hot campfire, okay? So if you combine those previous relationships that we talked about, the proportions, how things are proportional to one another, you can derive a single simple relation, pressure and volume being proportionate to temperature. So what about the amount of gas present? So now we're going to add whatever the amount, or the quantity of the gas that's present. So if the temperature and pressure remain constant, the volume is going to be proportional to the amount of gas. Okay. So we're working our way, as you see, we're working our way closer to PV equals nRT, which is the ideal gas law. 1 mole of a substance is defined as the number of grams of the substance that is numerically equal to the molar mass of the substance. Well, what does all that mean? That means you're going to need a periodic table, or you're going to need to be given the common masses of certain things. So 2 moles of hydrogen has a mass of 2 grams, right? 1 mole of neon has a mass of 20. CO2, carbon dioxide, you have 1 mole of carbon and 1 mole of O2, right? So 1 mole of oxygen, right, is 16. 16 times 2 is 32, right? 1 mole of carbon is 12. 16 plus 12 is 44. So the number of moles in a certain mass of material is number of moles is equal to the mass in grams divided by the molecular mass, as in grams per mole. Okay. That's important because that's the equation we're going to use in PV equals nRT. That is the number of moles of the substance. Okay, so now we can write the ideal gas law. PV equals nRT. N is the number of moles, calculated this way. And R is the universal gas constant, which is 8.314 joules per mole Kelvin. Okay, this is why you need your temperatures in this equation to be in kelvins. Now, in your chemistry class, you may have had a different variation of this using a different constant and a different temperature scale. I get asked questions all the time. Can I use that if I know that better? Absolutely, you can. If you get to the same answer, awesome. This is the way I'm teaching it, but there's more than one way to get there, okay? So let's take a look at an example. Standard temperature and pressure, STP, okay? STP, standard temperature, is going to be 0 degrees Celsius, which is 273 degrees Kelvin. Standard pressure is 1 atmosphere, which is 1.013 Newton per meter squared. It's also equal to 101.3 kilopascals. They want us to determine the volume of 1 mole at STP. Determine the volume of 1 mole of any gas, assuming that it behaves like a gas at STP, which is standard pressure and temperature. Let's go to a whiteboard and run through this quick. So they want us to find the volume. So using PV equals nRT, if I solve it for volume, now again, you can plug the numbers in,
up here and then just do the algebra, or you can do the algebra first, whatever you want to do. So they want us to determine the volume of 1 mole. So we're already given the number of moles, 1 mole. R which is your universal gas constant, which is 8.314 joules moles per Kelvin. So take a look at the constants that you're given and just recognize that the other things in the equation are going to have to be in those units. So like for the universal gas constant, you have moles. So your M, your number of moles, has to be in moles, right? Temperature has to be in kelvins because that constant is given in kelvins. So 273K. Standard pressure, again, is 1.013 Newton per meter squared, or 101.3 kilopascals. So 1.013. So on the previous slide, it should be 1.013 times 10 to the 5th, right? The times 10 to the minus 5th is missing. So it should be 1.013 times 10 to the 5th. Newton per meter squared. Okay. This volume works out to 22.4 times 10 to the 3rd meters cubed. If 1 liter is 1,000 centimeters cubed, (1.00 times 10 to the minus 3rd meters). So one mole of any ideal gas at STP is 22.4 liters is the volume. So this is just a unit conversion to get from your meters cubed to your liters. Oh, I made a mistake here. This should be 10 to the minus 3rd meters cubed. Okay. Should be 22.4 times 10 to the minus cubed. And then when you do this conversion, you get to your 22.4 liters. Sorry about that. Okay. So, helium balloon, example from the very first slide. Well, this is a smaller balloon, party balloon. Small helium party balloon, assuming to be a sphere, has a radius of 18 centimeters. Room temperature is 20 degrees. Its internal pressure is 1.05 atmospheres. Find the number of moles of helium in the balloon and the mass of the helium needed to inflate the balloon to these values. Okay. So the volume of a sphere, 4/3 pi r cubed. So if I want the volume of the helium, 4/3 pi, and they told us that the radius of the balloon is 18 centimeters, which is 0.18 meters, and that's cubed. So our volume is 0.0244 meters cubed. If we're working with PV is equal to nRT, I want to solve for the number of, so it says find the number of moles of helium. So I'm solving for N, which is going to be pressure times volume divided by universal gas constant times temperature. We were given that 1.05 atmospheres is the pressure. But we want to be working in Newton per meter squared. So if I do the conversion of this, given what I know, you get 1.064 times 10 to the 5th Newton per meter squared. So I'm just taking my 1.05 in atmospheres, and I am multiplying it by the 1.013 times 10 to the 5th Newton per meter squared to get that, to get my pressure. So this is the pressure. So now I have everything that I need to plug into this, right? So the number of moles is going to be my 1.064 times 10 to the 5th Newton per meter squared. I'm going to multiply that by the volume, which I figured out in the first step, 0.0244, whoops, 0.0244 meters cubed divided by universal gas constant, 8.314 joules per mole Kelvin. So Kelvin, I'm given 20 degrees. To convert it to Kelvin, I'm given 20 degrees C. To convert it to Kelvin, I add 273. So this is going to be 293. So the number of moles is 1.066 is the number of moles of helium. So find the number of moles of helium. So there's my number of moles. And the mass of the helium needed to inflate the balloon. Well, we know that helium has a mass of 4.00 grams per mole. So the beginning of the textbook, inside your, I believe it's the first cover, the back cover. The back cover of your textbook has a periodic table of elements, and in there it has the masses, and you'll find the 4.00 grams per mole there, or on a test it would either be given to you or you'd be given a photocopy of a periodic table. So if you have the number of moles and you know it's 4 grams per mole, the mass of helium that you need is 4.26 grams. Okay. So let's do another example. Mass of the air in a room. Okay. So estimate the mass of air in a room whose dimensions are 5 meters by 3 meters by 2.5 meters at STP. Okay. Now, on this example, I'm going to make some assumptions about the problem. Okay. One of the assumptions that I'm going to make, and on a test, I wouldn't ask you to make these assumptions. I would give you more concrete information. But to fill in the blanks on a textbook problem like this, air is not 100% oxygen. Air is only about 20% oxygen, and roughly, we're going to call it 80% nitrogen. That's high. So is the oxygen. There's other things, but it's small enough that we can ignore it. So we're going to say 80-20 oxygen and nitrogen is what the air in this room is made up of. And we know from the previous calculation that 1 mole has a volume of 22.4 liters, which is 22.4 times 10 to the minus third meters cubed. So we're going to recycle that with this example also. So I'm going to clear this. All right. We want to determine the volume. So the volume of the room was 5 meters by 3 meters by 2.5 meters. So the volume of the room is 37.5 cubic meters, or meters cubed. Okay, so I got my volume. The volume of the room, but we need to find the volume of the gas in the room, right? So at STP, which they gave us, so this is the room, this is the gas. We're going to say 22.4 liters, which is 22.4 times 10 to the minus third meters cubed. Okay. So if I do my 37.5 meters cubed divided by the number of moles per 22.4 times 10 to the minus third cubic meters. So we end up with 1674 moles, or roughly 1,700 moles. Now, we know that N2 is 80% of the room, based on what I was saying before, and O2 is only about 20% of the room. Now, like I said, on a test, this would be given to you. So you have 2 moles. Each mole of nitrogen is 14. That's 28. You have 2 moles of oxygen, which is 16 per. That's 32. The average between the two is 29. So that kind of puts me halfway in between here. Okay. But I need to break this down Um, so the 29 becomes so 1 mole is going to be 29 mu, which is equal to 0.029 kilograms per mole. And if we know that there's roughly 1,700 moles from here, and we know 0.029 kilograms per mole, the mass is roughly 50 kilograms, which is about 100 pounds of air in a room if you were to pump it out, or if you were to measure it. So other ways
to solve ideal gas law problems. The volume of 1 mole of an ideal gas, again, 22.4 liters. So the amount of gas will not change, okay? Always measure temperature in kelvins, and pressures must be absolute pressure. So remember that absolute pressure is atmospheric pressure plus gauge pressure, okay? Atmospheric plus gauge. Okay. A lot of newer cars have sensors on them that tell you when the tire pressure is going down, okay? And they're calibrated such that if you have a slow leak, you know about it before you end up with the tire blowing out and creating a possibly dangerous situation. A lot of times when you have the first cold snap or the first cold day morning of the year, if you go to Wawa or Sheetz to get your cup of coffee, you'll see 15 cars in front of the air filling station because everybody's low tire pressure light came on, because there's only about 3 to 5 PSI before that light comes on and says the tire pressure's low. So an automobile tire is filled to gauge pressure of 200 kilopascals at 10 degrees C. If you drive 100 kilometers and the temperature within the tire rises to 40 degrees C, right? What is the pressure in the tire now? Okay, so I'm going to stop sharing here. And I'm going to go to the whiteboard. Clear this, right? So what we were given, P1, V1 over T1 is equal to pressure, volume, and temperature, okay? So we know from this example, right, there will be no change in the volume. Okay, so V1 is equal to V2. So V1 and V2 will cancel. So if I want the pressure after we've driven, I'm just solving for P2 here, right? It is going to be P1 times T2 over T1. So P1
we were given that the gauge pressure, when you measured the gauge, was listed as 200 kPa. Okay. But to get to absolute, which was what we just talked about, we have to add atmospheric pressure, which is 101 kPa. So you end up with 301 kPa if 1.013 times 10 to the fifth Newton per meter squared is the units we want to work with. That is equal to 101.3 kPa. If I want to convert 301 kPa to units of Newton per meter squared, which is what I need to use this equation, it's 3.01 times 10 to the fifth, right? So P2 3.01 times 10 to the fifth. Temperature 1, 313, because I'm converting my temperatures to kelvins. So you want to be working in kelvins here. P2, if you work this out, you get 333 kPa. Again, that is total pressure. If I subtract atmospheric pressure, my P2 or P gauge 2 is going to be 232 kPa. So P1 is 200. I end up with 232. It's about a 16% increase in what is shown on the gauge. Since the gas constant is universal, okay, the number of molecules in 1 mole is the same for all gases. That number is called Avogadro's number. Avogadro's number, capital N, 6.02 times 10 to the 23rd. So Avogadro's number is equal volumes of gas at the same pressure and temperature will contain an equal number of molecules. Okay. 6.02 times 10 to the 23rd, Avogadro's number. Here's another way to look at ideal gas law, PV equals nRT, using something called the Boltzmann's constant, which is your ideal, your universal gas constant divided by Avogadro's number. It's just another way to use it. I am more familiar with PV equals nRT. Again, you might be more familiar with that previous methodology. So hydrogen atom mass. Use Avogadro's number to determine the mass of a hydrogen atom, and then how many molecules are in one breath. Estimate how many molecules you breathe with 1 liter, with a 1 liter breath of air. Well, the first one is pretty easy. Right? If we want to know the mass, we know that oxygen from a periodic table, 1.008 or 1
times 10 to the minus third kilograms per mole, right? And we know Avogadro's number is 6.02 times 10 to the 23rd. That's the number of molecules are in 1 mole, right? So it is going to give us kilograms per molecule. So it's 1.67 times 10 to the minus 27th kilograms. So how many molecules, that's the mass of a hydrogen atom in kilograms, right? Not the kilograms per mole. So how many molecules in one breath? We know from STP, 1 mole, 22.4 liters, right? If you have 1 liter and you know that there are 22.4 liters per mole, you get 0.045 moles. But how many molecules is that? Well, Avogadro's number is the number of molecules per mole. So if we have 0.045 moles, and we multiply this by Avogadro's number, 6 times 10, or 6.02. .02 times 10 to the 23rd molecules per mole, you get 3 times 10 to the 22nd molecules in 1 liter, in a 1 liter breath of air. There's 3 times 10 to the 22nd molecules. Ideal gas law, temperature scale, and standard. So the standard uses the constant volume gas thermometer and an ideal gas law. So there are 2 fixed points. You have absolute 0, right? And the pressure is 0 at that spot, right? You can find what is called the triple point of water. The triple point of water is where all 3 phases can coexist. It is defined to be at 273.16, just under absolute 0. So the pressure here is 4.58 torr. That's not really going to be on the test. Neither is this. So chapter 17, all matter is made up of atoms. Atomic and molecular masses are measured by atomic mass units, or U. The temperature is a measure of how hot or cold something is and is measured by thermometers. There are 3 temperature scales, Celsius, Fahrenheit, and Kelvin. If you heat them, a solid will get longer by a fraction given some coefficient of linear expansion. That's thermal expansion. You can also have the same thing for gases, a fractional change in volume. For gases and liquids is given by volumetric expansion. Ideal gas law is PV equals nRT. 1 mole of a substance is the number of grams equal to the atomic or molecular mass. Each mole contains Avogadro's number of atoms or molecules. That is the end of chapter 17. Stay tuned for chapter 18. Please take a look at the recommended problems. They are a good representation of what you can expect level of difficulty wise on an exam. Please continue to come to the Zoom meetings. Again, if there are any requests for additional Zoom meetings, just send me a day and time and I will do my best to accommodate you. So come prepared with questions, and good luck, and we'll talk to you soon.